Thank you so much. Yeah, thanks for the organizers for this wonderful conference and for allowing me to present this talk. Today, I'm Christian Ginski. I'm a postdoc at Leiden Observatory, and I will be talking about imaging the cradles of planet formation with the Sphere Destinies large program. And just to say, all of the results that I'm showing today are a huge team effort by a large number of collaborators that I've just listed here on the bottom of this page. To put the objects I'm talking about in context, this is the standard picture of star and planet formation. And on the lower left, we have the face of the protoplanetary, or as we should probably rather call it, the planet-forming disk. This is right after the protostellar envelope has evaporated and the disk becomes visible in the near-infrared and optical wavelengths, and lasts for about 10 million years until the gas in the disk has dissipated. The observations in Sphere Destinies are conducted at the ESO-VLT with, as you may have guessed, the Sphere Extreme Adaptive Optics instrument. One major issue that we have in the infrared is that we are dealing with a very bright star in the center of our image that we are usually not so interested in, and we would like to see the faint circumstellar environment. So to do this, we have to somehow get rid of the stellar light, and the predominant technique for this is polarization differential imaging. Here we're using the fact that the central star's light is on average unpolarized, whereas the light that gets scattered of small dust particles in the upper atmosphere of the circumstellar disk becomes partially linearly polarized. So by using a combination of polarization filters and clever subtraction of images, we can get rid of the stellar light but retain the light from the circumstellar disk. Scattered light observations can trace the interactions of planet with their parent disk. Here I'm just showing you a simulation of a gas surface density map on the left from Zhang et al. 2018, where a 3 Jupiter mass planet was introduced into the gas and it's producing these beautiful spiral density waves. Together with my former PhD student, Gabriela Moro-Arena, we took these simulations and we produced, we added dust and we produced simulated scattered light observations. And this is what those scattered light observations look like. And you can see that you can still trace these same spiral features in scattered light. This is because the micron-sized dust that we are observing predominantly is very well coupled to the gas in the disk. And we actually found some observations also not too long ago that Gabriela was leading in the SR21 system that look very strikingly similar to these simulations with this double spiral structure in the SR21 system. So now that I've shown you that we can trace the interaction of planets with the disk and scattered light, the question that I'm asking is there a typical evolutionary pathway for a planet-forming disk to go from a smooth protoplanetary disk that we see here on the left to a structured planet-forming disk on the right? And how does this evolution and then ultimately the planet formation depend on the stellar and disk properties? And to answer these questions, we started the Destinies program. Destinies stands for Disk Evolution Study through Imaging of Nearby Young Stars. It's an ESO-large program. We got granted almost 128 hours of telescope time, and we're observing 85 T-Tauri stars in nearby star-forming regions. We are scattering throughout several star-forming regions because we want to cover a range of ages, roughly from the youngest objects, younger than a megayear, all the way up to 10 megayears. And we are predominantly targeting objects that have so far not been observed with imaging observations because they're a bit difficult, because they're faint in the optical typically, so difficult for wavefront sensors and so on. So objects that are a little bit lower mass than stellar masses, down to about 0.5 solar masses typically. We have also expanded this program in the meantime to have a more holistic view of the systems with the Destinies X program, where we use VLT X shooter to get high resolution UV to near infrared spectroscopy to characterize the central stars and their accretion properties, and the Destinies Millimeter program, where we use ALMA to obtain snapshot observations in the millimeter continuum and CO gas lines to trace the bulk mass content of those disks. And these are some of our ongoing observations that we have obtained. We still have about a third of the program to carry out this year. And you see there's a huge diversity in structures that we are tracing, from these very smooth, flared, almost archetypal disks to disks where we see clear interaction with binary stars and disks that are still interacting with their surrounding cloud material. And we're very, very fortunate in the Destinies team to have many young and enthusiastic students. I just want to highlight there's several studies that are currently on the way led by these students, from scattered light detection of a disk wind to radiative transfer modeling of disk swaps that we're observing, all the way to improving of data processing, which will ultimately, hopefully, lead to detection of planets within the DESTINY's data sets. One of the most spectacular early science results from DESTINY's are the observations of the SU-Auriga system. Here you see the polarized scattered light observations in the H band, so it's at 1.6 micron. And you can tell, so there's a central disk, and then there's these huge, beautiful streamers attached to the disk at very large scales. And I want you to pay particular attention to the streamer in the north, which from the scattered light observations we can tell is behind the disk, and the streamer in the west, which we can tell is within our line of sight in front of the disk. And we combined these observations in scattered light with archival AMO observations, where we can see in particular the gas in the disk and see how the gas is moving in the disk. And with that, we could show that the material in the northern streamer is blue shifted relative to the central system velocity, so it's falling toward us. The material in the western streamer is red shifted, it's falling away from us, so all of this material is falling onto the disk. So we have an example of late material infall onto a disk. And we can already trace in our images the result of this material infall. So what we see here in the scattered light is this dark bar that is going across the disk, and that is a shadow that is visible here due to a misalignment, a very strong misalignment of the inner unresolved disk and the outer disk that we are tracing in scattered light. So this outer disk is the disk that all this material and resulting, of course, the angular momentum is falling onto. And we think that this will tilt the outer disk with respect to the inner disk and produce this misalignment. And there's actually a beautiful interferometric measurement from Aaron Lapdon from 2019 already, where the inner disk was resolved in the K band. And if we're using the orientation that was obtained from the interferometric observations, then that matches beautifully with if we combine it with the outer orientation of the disk to produce this shadow lane that we are seeing in the scattered light. And these infalling observations, if this is a common process among young systems, then that might well explain spin-orbit misalignment we see in evolved planetary systems, because this is a very nice way to tilt part of the disk. And then if planets are forming in this disk, their orbits will, of course, be misaligned with the central spin of the star, and that might very well explain this population that is found in radial velocity studies. I would also very quickly like to highlight a second result that came out only very recently by a paper led by Jane Huang on the complex environment of Dio Tau. So here we have the central star, Dio Tau, just highlighted as this tiny little star, and we will see that we are tracing structures at very different scales at different wavelengths. Starting out with HST STIS observations, so this is archival data that we added to our DESTINY's observations, where we see this large northeastern arc here, so a very large scale arc structure in scattered light. Then we added AMO observations with very high velocities, where we see an outflow, a red and blue shifted outflow in the system. Then if you go to smaller velocities, closer to the system velocity, you start seeing streamers in the gas that are going here to the east. And then finally, when we add our sphere scattered light observations, we are looking at the smallest scales, where we see a northern and an eastern arm that is connecting to the circumstellar disk, and the circumstellar disk appears smooth and relatively strongly flared. And in this paper, we are speculating on the origin of those structures. So there's Dio Tau is very nearby the HV Tau system, and if you look at Herschel observations, then it looks like there's a bridge between the two systems. So it might very well be that the complex environment that we're tracing is a result of the encounter between these two systems, and material is actually stripped from Dio Tau. On the other hand, we might just trace the remnant material from the original embedding cloud around Dio Tau. And both of this has different implications, for example, for the mass budget that is available for this disk, for planet formation, and so on. So this brings me to my conclusions and my take-home messages. So first of all, in this very short talk, I hope I could show that high-resolution imaging in the infrared is a very powerful tool to study the earliest phases of planet formation. The scattered light observations can actually trace the interaction of planets with their natal disk. We find a large diversity of these structures already in our program. And of course, it was already found to a larger extent in previous observations. these young systems that we are looking at now should ideally not be studied in isolation. So if you start looking at the DO-tau system just with unresolved photometry and you're treating it as your archetypal flared young disk, then you might run into issues, because what we're now seeing is that there's really a very complex interaction with the surrounding environment. And this complex interaction can be traced with panchromatic observations, ideally at multiple scales. And then what happens due to this interaction with the environment will, of course, influence the planets that ultimately form in those disks. Like, for example, the late infall material in SE Auriga might well lead to spin-orbit misalignment in the planets that are eventually forming in this system. Stay tuned in the next few months, hopefully, for several more of these Destinies papers to come out. And in the meantime, I'm happy to accept any questions. Thank you.
Thanks, Christian. Any questions for Christian? Yeah, you can go ahead.
So for the late info model, can you estimate the info rate from CO observations for both sources?
Right. We did not really do this for SE Auriga, because the problem is we have mostly the detection in 12 CO and some detection in 13 CO, but we think we're still optically thick. So we are probably not good at calculating the actual mass that is infalling. There's now several follow-up studies to obtain optically thinner tracers, proposed follow-up studies to obtain optically thinner tracers, so that we can actually obtain this info rate. Same or similar is going on for DO-tau to an extent, where we have marginal detections in the optically thinner tracers compared to the optically thick tracers.
Any more questions? No question? Yeah, go ahead.
Hi, Stefan here. On the idea of having the misaligned late infall to produce a misaligned hot Jupiters, do you know how extreme you could make the misalignment? So could you even produce retrograde orbits?
So the misalignment can be quite extreme. I mean, in the case of the SE Auriga system, it's, I think, on the order 70 or so degrees. So between the inner and the outer disk. So you can easily produce extreme misalignments in this way, I think.
Mm-hmm. But for retrograde, you would even need to go beyond 90 degrees, and
right,
the kinematics would work then. So
that is true. I mean, that I'm not 100% sure. I mean, in principle, I don't necessarily see why it couldn't be possible off the top of my head, but yeah, it would obviously depend on the amount of material that's falling in and the amount of angular momentum transfer. So not sure is the answer, but I would not exclude it.
Mm-hmm. Thank you.
Yeah, if there are no further questions, we can thank Christian again.